San Francisco's Bay Bridge opened in 1936 and proved wrong all those who said the river was too wide and deep to bridge. Spanning 8¼ miles, it was and still is a marvelous feat of engineering. Interestingly, its design includes a lot of triangles. Commonly, structures that must be strong and stable, such as bridges, rely on an underlying triangular framework. That's because their stability is based on one special property of the triangle, that the length of its sides determine its exact shape. So, if the sides have stable lengths, the shape cannot change. That's why triangles can be classified by their sides and angles. They have 3 sides and 3 angles. The sum of the measures of their interior angles is always 180 degrees. The sum of the lengths of any 2 sides is always greater than the length of the 3rd side. And the lengths of its sides uniquely determine its shape, including its angles. Let's test one of those properties. This triangle has 2 sides, both measuring 10 feet. The sum of these 2 sides is 20. What would happen if the 3rd side was longer than the sum of the other 2, or greater than 20? Well, the 2 shorter sides together could never reach the ends of the longer side. There would be a break between them and the 3rd side. As a result, the structure couldn't be a triangle because a triangle is always a closed figure with 3 straight sides. Of course, we can change the lengths of the sides and their angles and then end up with a triangle. It just might be a different type of triangle from the one we started with. But the sum of the lengths of 2 sides must always be greater than the length of the 3rd, and the sum of the measures of its angles must still be 180 degrees. Triangles can also be combined to form other shapes. See how the Bay Bridge's deck girders have triangles that share sides to form parallelograms and trapezoids? Even though the triangle is a fairly simple geometric shape, its properties and possibilities are many and varied. Let's look further at properties of the 3-sided polygon called the triangle. What do densely populated cities tend to do when they're feeling crowded and looking to expand? Build up, of course. Tokyo, one of the most densely populated cities in Asia, plans to construct a 3-dimensional city in the sky that would house 750,000 people, skyscrapers, homes, parks, and businesses. Engineers and architects have designed what would be the largest structure on Earth if ever built. And they've done so with a triangular framework based on the ancient pyramid structure. Tokyo's city in the sky would be 12 times larger than the Great Pyramid of Giza. Comparing them can help us understand the triangle's unique properties. Look at the face of this pyramid. What makes it a triangle? It's obvious that it has 3 sides, and it has 3 interior angles. But what about those sides and angles? The angle at the top is 76.4 degrees. The 2 on the bottom are both the same. So the sum of the 2 at the bottom is 180 minus 76.4, which equals 103.6 degrees. Since they're the same, each one is half that, 51.8 degrees. This triangle has 3 equal angles. 1/3 of 180 is 60. Each one is therefore 60 degrees. If all 3 angles of a triangle have the same measure, their sides will all be the same length too. And it's called an equilateral triangle. What if you're told a 3-sided object has sides measuring 6 feet, 8 feet, and 1 foot? Can it be a triangle? Let's check. The length of the longest side of a triangle must always be less than the sum of the lengths of the other 2 sides. But 8, the measure of the longest side, is more than 6 plus 1. That means the length of the shortest side, 1, is also less than the difference between the other 2, 8 minus 6. That doesn't work. So if we try to make a 3-sided figure with sides of those lengths, it's easy to see that either the sides don't connect or the longest side is curved. Either way, it does not make a triangle. At the point where the sum of the lengths of two sides equals the length of the third side, the triangle is stretched out so far that it's not a triangle, but a single line segment. The angle between the two short sides is itself 180 degrees, leaving no room for the other two angles, which would be 0 degrees. The sides are all on top of one another, therefore no triangle. Boats and planes traveling over the Atlantic used to dread crossing this spot for fear of disappearing into thin air. Legend has it that when Christopher Columbus sailed here, his crew saw weird lights and his compass went haywire. It's been called Limbo of the Lost, the Twilight Zone. But today we know it as belonging to Bermuda and possessing properties of a three-sided polygon, the Bermuda Triangle. This three-sided section of the Atlantic Ocean, with Bermuda, Puerto Rico, and Miami as its vertices, used to be legendary for swallowing anyone who tried to pass through it. It's just a myth, but it is a triangular section of the ocean, so it can keep its name. The sum of the measures of a triangle's interior angles is always 180 degrees. We can label the angles on the Bermuda Triangle A, B, and C, and put their measures into an equation. Measure of angle A plus measure of angle B plus measure of angle C equals 180 degrees. If we know the B and C angles of the Bermuda Triangle measure 62 and 63 degrees, what's the measurement of the third angle? Plug the B and C measurements into the formula. The calculation shows that the A angle measures 55 degrees. Triangles are all around us. Take a look. From bridges to sailboats to hang gliders. Though triangles are seemingly everywhere, they're not all the same. Not every triangle has 3 equal angles and 3 equal sides. Only equilateral triangles do. All interior angles of an equilateral triangle measure 60 degrees, and all sides, no matter how small or large, are the same length. Another special type of triangle is an isosceles triangle. 2 of the angles are equal in an isosceles triangle. The sides opposite those angles are also equal. If this triangle has an angle that is 40 degrees and another that is 70 degrees, how can we tell what kind of triangle it is? We know it's not equilateral because it already has 2 angles with different measurements. And we know that equilateral triangles have all angles equal. The 2 measurements we do have add up to 110 degrees, which means the last angle must be 70 degrees. Since 2 angles of our triangle both measure 70 degrees, then the sides opposite those angles are also equal in length, which means we've got an isosceles triangle on our hands. Triangles that are not equilateral and not isosceles, meaning they have 3 different lengths of sides and 3 different angles, are called scalene triangles. See how considering relationships among angle measurements or side measurements can be used to learn more about some triangles?